Most of us know Carl one way or another, either personally or through the mentorship of his outstanding teachers and researchers and practitioners throughout the industry. He has literally established the landscape. If I may make a pun here, he's sort of paved the way for many of us. He is a true leader in flexible pavement design and analysis. Errol talked about 5 decades. It's probably closer to 6 that he has led. I kind of claim as being a member of his academic family because my major professor was John Epps. John Epps was a student, of course, of Carl, as was his daughter, Amy Epps Martin, who was my son's mentor in graduate school. So, although not directly, indirectly, I claim being a member of his academic family. Wonderful person, wonderful individual, as well as a great researcher and leader in our area. I want to mention the names of many people who have helped me through my career. Certainly Errol Tutumler would be one of them, a brilliant researcher that I've had an opportunity to work with. But since Errol's already introduced me, I'll just leave it at that. I'm not going to try to name the others simply because if I name some, I'll leave some out. And I'll hate myself in the morning for leaving people out. So I'll just simply list, if you will. Oops, I don't want to do that. I will list the institutions where I gained my educational background. In each institution, there are wonderful mentors, there are wonderful colleagues that help me through. Throughout my lecture today, I'm going to mention a number of students who have been instrumental in producing some of the deliverables that I'll discuss. And I'll try to give them credit. I can't claim that in all cases I have given them proper credit on the slides, but at the end of the lecture, I'll certainly call out their names. My topic today, my lecture, is going to be essentially pavement analysis based upon mechanics principles and material science. Now, I'll tell you to begin with that I am not a computational mechanics expert, nor am I a true mechanics expert. I understand mechanics to this level. I know when to go out and seek an expert. I think I understand at least the application of mechanics, but when it gets into the weeds, then I'm going to need some help, and I've surrounded myself with some really good people. But one of my topics is going to be the application of some of these mechanics to pavement analysis. That's what we did in the ARC program that Errol mentioned, the Asphalt Research Consortium. In the ARC program, we developed one deliverable that we call Panda. The acronym Panda, as you see here, which stands for Pavement Analysis Using Nonlinear Damage Approach. In the Panda model, we evaluated the performance, or we came up with a tool that evaluates the performance of asphalt pavements by integrating a lot of the materials science and the materials engineering that I claim to be my strongest point. It may not be strong compared to other experts, but it's my strongest point and my point of interest. So I'll try to talk about that as we move through our discussion. As I just mentioned, peppered through this discussion of pavement performance using the Panda model, which will be sort of a template for my discussion, I'll talk about some of the materials science and some of the materials engineering that went into some of the basic concepts that we apply throughout the Panda model. And then finally, I'll wrap it up by changing gears a bit and talking a little bit about geochemistry and the application of geochemistry to understanding some of the problems that arise in one of my favorite subject areas, and that is chemical soil stabilization. We have problems in chemical soil stabilization. Sometimes the problems are simple, sometimes the problems are great. And when we try to solve those problems, we really have to go to a basic understanding of the geochemistry and the material science behind it. That's where I get a lot of kicks. That's where I have fun. Now let's go back to the basic analysis of a flexible pavement system. And this basic analysis is the tool that we're using is called Panda, which is a a computational model of the pavement structure. In the constitutive relationships within Panda, it's important that we characterize the asphalt as nonlinear, viscoelastic, and viscoplastic. Nonlinear, viscoelastic, and viscoplastic. Besides doing that, we have a number of state variables that help define the response of the asphalt. And I've listed those state variables here. The first one, the Q term, is simply a definition of how the failure surface changes. It's a dynamic failure surface. So when we calculate damage, we're calculating damage against a moving failure surface that hardens with load applications, and if there's an extended rest period between or among load applications, there's a bit of a relaxation. So this state variable that defines the movement of the failure surface has a hardening function that moves it forward, makes it stronger, and it has a bit of a relaxation function in it as well that we have determined is required over a long time of research. The second state variable here is the capital phi term, which is damage. Now, I'm going to talk in just a few minutes more about damage. The way that damage occurs in the model that we're using, which is a continuum damage model, continuum damage mechanics-based model, is that we develop a system of what we are microcracks that are due to the excessive stress level. And those microcracks compromise the area that's taking the load in this particular sample. The third state variable is that of healing. We use the little term H for healing. And through many years, I've worked on healing in asphalt for many years, beginning with Professor Richard Kim when he was my student at North Carolina State. He's a distinguished professor there now. And he did his PhD dissertation on viscoelasticity and healing. At that particular time, nobody really believed in the microcrack healing process, but now, for example, at Delft University, they had an entire institute, or consortium, I should say, which dealt with healing and put out a lot of excellent work. So we believe that microcrack healing is important in the fatigue process, and it's one of the state variables that we consider. And then there is the phi with the superscript moisture, which stands for moisture damage as moisture diffuses into the matrix of the asphalt and compromises the cohesive strength as well as the adhesive bond strength. And then finally, the last state variable is aging. You can see down here when I talked about the moisture moving into the system, the asphalt composite, it compromises the strength of the mastic, and when it gets to that interface, it compromises the adhesive bond as well. When aging occurs, aging stiffens the mixture. It stiffens the mixture by oxidative aging, by hardening, and makes it often more susceptible, less susceptible to plastic deformation, but more susceptible to the process of fatigue damage. So our model, Panda, is a nonlinear model, and it characterizes the asphalt as nonlinear, viscoelastic, viscoplastic. The model that we use for the nonlinear viscoplastic or viscoelastic portion is a model that was developed in the late 60s by Dick Shaprey at Texas A&M. And the G terms in this particular model define the level of the stress sensitivity that makes it nonlinear. The first G sub naught modifies the initial compliance, the elastic response. The terms after the integral, or just before and after the integral, G1 and G2, modify the transient compliance response. And of course, we have a time temperature shift factor involved in this calculation of the viscoelastic properties. And we find it more convenient to model the transient compliance using a Prony series where d sub n represents the coefficient and the lambda sub n represents the relaxation times in the Prony series that define the viscoelastic response is defined by the Kelvin systems, a series of Kelvin systems in the model. So we accommodate viscoelasticity, to make a long story short, and we accommodate nonlinear viscoelasticity. So how does Panda deal with rutting? How does it deal with plastic deformation? Well, I'm taking some pretty complex processes and trying to simplify them, trying to boil them down to some simple discussion here. And sometimes it's very difficult to get too simple in some of these models. But what Panda does is it accounts for the viscoelastic component of strain, as we just discussed, and it also accounts for a non-recoverable, a viscoplastic component of strain, and that's what causes rutting to occur. So the viscoplastic component of strain is accounted for by a Przina type model. In 1971, Przina and his cohorts, his colleagues, came up with a model that defines the rate of viscoplastic strain. And that function looks like this. It looks pretty complex, pretty hairy, but basically it starts off with an initial identifier of the rate of initial deformation, plastic deformation. That's the lambda superscript VP term. And then within the brackets here that are called Macaulay brackets, there is a function, a different phi function times F, which is called an overstress function. And essentially what this term does, it identifies the stress point. If the stress point is behind the yield surface, and you can see the dark curve here, that's the yield surface. If it's within the yield surface, no plastic deformation occurs. No plastic deformation occurs. It simply does not develop rutting. If it occurs outside that yield surface, then plastic deformation occurs. And the magnitude of that plastic deformation is related directly to the magnitude of the overstress function, corrected by the direction of that overstress function. So this is a fairly complex looking animal, but that's the way we characterize plastic deformation using a Przina type model. You might also note that in this relationship, the yield surface, which is defined here as F, is something that is a function of a shear stress, the I sub 1 first invariant, which is the confining pressure, times alpha, which is the internal friction, so that's a Drucker-Prager type relationship. And it's modified by the hardening function out here, the K sub, kappa sub P. So that defines the yield surface, and it is a dynamic yield surface, which hardens with loading, and with long-term relaxation between loads, there's a bit of softening that can occur. Dynamic yield surface. Okay, so how does Panda deal with damage? How does Panda deal with damage? Well, just looking at the equation here, it's pretty complex, but we can simplify it down by talking through it. The driving force for damage is nothing more than this Y term, which is this Drucker-Prager type of a relationship between the shear stress that's developed minus the angle of internal friction times the confining pressure, I sub 1. And if you look within this relationship, the yield stress is also defined by whether the process is an extension or contraction. That's the D term. And the ratio of J sub 3 to J sub 2, which are the second and third deviatoric stress invariants. So it accommodates a number of stress states to define whether or not a yield function or a damage force will be activated And basically speaking, if the confinement stresses are such that they keep the yield stress or the shear stress intact, or they prevent it from developing, then the Y force will be very small. The driving force for damage will be very small. If, on the other hand, the deviatoric stresses overcome the confining pressures to a large degree, the Y parameter becomes large and the damage force becomes great. Now, so we've got a way to calculate damage. And this damage we're looking at is really, we're viewing it as a series of microcracks that are compromising the integrity of the area that is resisting load using continuum damage mechanics. The Y function, which is driven by shear stresses and which is mediated by confining pressures, drives this damage force. There's something that's working against this damage force, and that is healing. Now, several years ago, one of my students, Professor Amit Bhasin, now Associate Professor at the University of Texas at Austin, looked into the work of healing in polymers. And he came up with some work by Professors Wool and O'Connor back in 1981. And they said that there is a convolution of processes that are occurring. So this parameter R, which could be recovery of stiffness, or it could be recovery of stress or strength. That's what R is a parameter related to stiffness or stress. That recovery during a rest period is a convolution of processes. And the first process is this term right here, which is related to the wetting of the cracked area. Now, my visual up here may be a little bit hard to see, but if you look on each side of a crack, this is an upper crack, that's a lower crack, I've got a bunch of molecules that are supposed to simulate the molecules that are typical in asphalt. If you could see it well enough, I think you would note that. Bottom, same thing. Well, when that crack is pushed back together, there's a wetting process that occurs. And that wetting process is directly related to the free energy of that cracked surface. That makes sense intuitively. Now, the other process that's going on here is that once the crack is closed, Josiah Willard Gibbs, I'm sure you somewhere along the line have heard that name, and you've probably taken some courses in thermodynamics. Einstein said that Josiah Willard Gibbs was the most gifted researcher in American history. And he came up with essentially Gibbs free energy, some of the basic rules of thermodynamics. So what's going on right here as the crack closes is that these molecules are reorganizing themselves, redistributing themselves to minimize the free energy, to lower that high free energy. And of course that free energy is high on two open crack faces because you've got so many incomplete bonds. So when they come back together, free energy is going to want to minimize, and that causes mobilization across the crack face. So we said, well, that's a great model for healing. And at about the same time, actually a little bit before that, Dick Shapery said, if you look at crack healing in a viscoelastic material, it's going to be a function of the size of the process zone, how big the crack is, the stress that will pull the crack back together, the viscoelastic compliance properties of the crack itself, how mobile is that crack to closing, how able is it to close, and surface free energy. So both claim that surface free energy has something to do with that wetting process and that healing process. So we looked at a number of asphalts in some of our early studies in healing with Amit Bhasin. And here is the response to healing. This is the percentage of healing. If you take an asphalt, you separate the asphalt and you allow it to come back together through a very nominal compressive force. and you allow it to heal. You measure the healing. I won't go into that. I don't have time on exactly how you do it. But you get an initial response, which is right here, which is pretty substantial, and then you get a time-dependent response. And if you come up with a general equation for that recovery of strength, this R sub h, you have the initial component, R sub 0, and then you have a time-dependent component, sort of a sigmoidal relationship, e to the power minus q times t to the r power. So you got a sigmoidal healing recovery process that's time-dependent. So this has to do with wetting, one would think, and this has to do with the reorganization of the molecules to lower the free energy. So we did some more research in that area, and certainly, or sure enough, what we found was that if we were to correlate this R sub 0 term for these 5 asphalts, by the way, they represent 5 very different compositionally different asphalts from the SHARP Strategic Highway Research Program. Some heavy in asphaltenes, some heavy in maltenes, some heavy in saturates and so forth. They're very different. And we also track those by measuring the surface free energy of those 5. And they rank, although there's not a lot of difference here, you can question the statistics here, but they rank right along with that R sub 0 term. The higher the free energy, the greater the initial wetting. Then we went one other step, and we used some dynamic simulation, molecular simulation, to evaluate how mobile the asphalt is. So we looked at different models of asphalt with different components of saturates and aromatics and asphaltenes and so forth, different polar components, to evaluate or try to model mobility. And how mobile is the asphalt as the crack closes to minimize free energy across that crack face. And what we found was not surprising, and that is the more mobile molecular structures, the greater the healing, and the faster the healing. So that gave us a lot of confidence. Let's go now to some work that was done by another PhD student of mine who's now assistant professor at the University of Kansas, and his name is Masoud Darabi. And Masoud has been of great help in helping us develop Panda. His brains are behind much of the complex mechanics. So what Masoud did in his PhD work was he looked at a controlled strain fatigue test. And of course he said, well, we're going to have a little compression in this controlled strain fatigue test because we're going to push the sample back together. This is a uniaxial sample. So we're going to pull a strain on it, we're going to push it back together, and during this tensile mode from A to B, of course we have a tensile stress, and when we go from A to B, the crack is becoming longer. The crack is becoming longer, fatigue damage is occurring because of increasing microcrack length. When this occurs, when we put the compressive mode into play from B to C, we develop a compressive stress in that controlled strain sample as we push it back together. And one would think that during that compressive mode, that maybe some of that crack that's pushed back together would re-wet, reorganize, and you'd develop at least a partial recovery in strength. So Masoud did some very careful work in a number of fatigue experiments, and what he found was that if we used our viscoelastic, viscoplastic damage model that we just discussed towards the middle point and the end of the experiments, what you would find is that the experimental data would look like the blue hysteresis loop, and the model would look like the red hysteresis loop, which is much flatter. You can see the angle if you draw a line from that point to that point and a line from that point to that point. the slope goes down, indicating that there's a reduction in stiffness and that there's more damage occurring in the model than would be actually seen in the experiment. When we put in a healing evolution function that sort of follows the trend that we just discussed, the healing evolution function, and I apologize, but I'm not getting much power on my pointer. There we go. The healing evolution function allows us to pretty much track the experimental data, the green curve and the blue curve. So what I've done is I've looked at the blue curve and I realize that's experimental data. The green curve is now the viscoelastic, viscoplastic damage model with the healing evolution function placed into it, and it tracks the blue curve much, much better than the red curve, which is the viscoelastic, viscoplastic damage model without healing. So this is kind of what the healing evolution function looks like. It's pretty complicated looking, but essentially it's this. It says that the rate of healing increases as temperature increases. This is sort of an Arrhenius function down here. As the healing increases, the rate of healing decreases. It's kind of asymptotic. And as damage increases, the rate of healing decreases. So it's a logical healing function and one that we use to correct for the effect of healing in the damage process in Panda. All right, now we've talked about some of the evolution functions for those state variables and how we view them in Panda. We've already said that Panda is a viscoelastic, viscoplastic model of the asphalt, and we can couple in healing. We don't have to use it, but we can couple it into the analysis. I'm going to skip now to the micro level from the general pavement mixture homogeneous layer level to the micro level, where we're actually looking at the structure of the asphalt. And so we would get that structure of the asphalt from some type of a imaging technique such as tomography. We would understand what the shape of the aggregate particles look like. And the blue in between the aggregate particle would be the mastic, the fine aggregate matrix. So in this particular micromechanical analysis, what we're doing is we're going to look at a component right up here of the mixture, and we're going to blow that component up. The aggregate is considered to be elastic. The blue material within the aggregate would be the fine aggregate, the asphalt in the fine aggregate, mineral filler and so forth. And you can't see it on this particular slide, but you've got a little blue interface, light blue interface, which is the adhesive interface. So we can characterize the nature of that adhesive interface as well. Adolf Fick is a name you should know because of Fick's two laws. Fick's first law is steady state diffusion. Fick's second law is a lot more complicated. It looks like this, and it's non-steady state diffusion. So diffusion occurs spatially as a function of time, according to Fick's second law. Adolf Fick was an MD, a medical doctor, but he had a high interest in physics, physical processes. So he looked at a whole bunch of data and he actually developed these laws. I think that's pretty fascinating. When we look at diffusion, and by the way, if you look at Fick's law, it's a bunch of second order differential equations. I mean, it's a second order differential equation, but the material science is in the D terms. The material science is in the D terms because that is diffusivity. And what we did very carefully in the ARC project was we measured diffusivity. Diffusivity of the aggregate, diffusivity of the mastic, and diffusivity of the mixture. You've got to have that to be able to understand how moisture diffuses into asphalt. Now, in this particular simulation, what you're seeing is that moisture diffuses, And as moisture diffuses, we're tracking the bond strength. The blue is the cohesive bond strength, or the strength of the mastic that's now being compromised because it's moisture laden. And the red is the strength at the interface, the adhesive strength at the interface. And you can see that they diminish as moisture increases into the sample as the moisture state becomes higher and higher. Now let's go a step further. Let's say that we are, and my animation's getting a little bit ahead of me here, but let's say that we're going to model something very simple. We've got an aggregate particle. We've got the blue mastic, another aggregate particle, the red interface, which is where the adhesion occurs, and we got an air void here. So that air void is now filled with water. It's saturated, and we've allowing diffusion to occur. If we apply a load to this material, and I'll try to back up. If we apply a load to this material, then the mechanical process coupled with the moisture diffusion allows us to envision the rate of damage. And you can see that when it's a saturated media, that rate of damage is going to be a whole lot faster because the hot colors represent a higher level of damage, the cooler colors, lighter colors, a lower level. When it's unsaturated, of course, the damage process is lower. And here's another view of the similar type of a situation. What we're doing here is we're looking at the damage process. We're blowing up this little section here in this micromechanical analysis, and the hotter colors represent the damage areas, so you can see that damage is occurring at that interface in most situations, which would cause stripping. All right, why did I show this? Well, I thought this was a good way to show you how Panda has the capability of taking mechanical damage and coupling the mechanical damage with the effect of moisture. So as moisture penetrates and diffuses into the system according to a recognized law like Fick's law, where we define the diffusivity, and we couple in the mechanical load with it, then we can visualize the damage process. We can do this at the mixture scale, the micro scale, or we can do it at the global scale or the pavement scale. What's the end result of something like that? Well, I'm getting ahead of myself. Hold on a second, I'll tell you. Let me go back one more step. We talked about some of the basic fundamentals behind adhesion. So we did a lot of work on looking at adhesion and how aggregates and asphalt bond together. So a little animation here. Let's suppose the red is an asphalt, A, and the gray here is a stone, S. So the work of adhesion between the stone and the asphalt, as I pull them apart, defines the bond strength. So if we know what the surface energy, which we can measure, of the stone is, and we know the surface energy, which we can measure, of the asphalt, we can actually calculate the adhesive bond strength. And here I've given you a little simulation. If you have a silica aggregate, then normally the high surface energy is because of these unbonded hydroxides. And so the asphalt is going to want to bond with that because of its polar components bonding with the surface of the silica. And that's what causes surface energy of both, the free bonds, and so that can be used to calculate the work of adhesion between the stone and the asphalt. Now over on the right-hand side is a little animation of what happens when water gets in the way. When water gets in the way, which is the blue stuff, we'll say that the gray is the asphalt and this is the stone, the water replaces that asphalt-stone interface in the the asphalt-stone interface. And when that happens, what you'll find is Gibbs free energy becomes negative. Gibbs-free energy becomes negative almost, virtually all the time. What that means, when Gibbs-free energy becomes negative, that process is spontaneous. So that means that water almost always wants to replace asphalt if it gets there. That's bad news. The magnitude of the negative value defines how strongly water wants to replace asphalt at that interface. So if we were to take a ratio of the bond strength in the numerator between the asphalt and the stone, and the absolute value, because this term is almost always negative, the absolute value of the work of adhesion of the asphalt and the stone in the presence of water, that energy ratio is something that we would want to be large. So we can measure the surface energy of the aggregate, the surface energy of the asphalt. We can measure them in the presence of water, and we can come up with this energy ratio that we want to be large. Because we want the dry bond strength to be great, we want the absolute value of Gibbs-free energy to be which is going to be negative, to be as small as possible, to make our system as good as possible. And of course, there's a picture of the hero here, Professor Josiah Willard Gibbs, who was the first PhD in the United States in engineering, to my knowledge. At least that's what Wikipedia says, and Wikipedia is never wrong, right? So Josiah Willard Gibbs was apparently the first PhD from Yale University and then went on to teach in material science. Here's a little data that just shows you that we can actually validate that that's the case. This is the ratio of resilient modulus in a wet state to the dry state, in the wet state to the dry state. Of course, the higher that value, the better it is. And this is the log of that energy ratio. So you want that number to be high. As that number is higher, you can see that the ratio of the wet resilient modulus is high compared to that of the dry. When that ratio is low, it's low. And these are 95% confidence interval bands, the dashed lines. So it looks like it's pretty good data. Down here is the same kind of data, except we're looking at permanent deformation. 1% permanent deformation. Once again, a high energy ratio, a higher number of cycles. This is cycles to 1% permanent deformation. So a high energy ratio, a better response. A low energy ratio, a poor response. So pretty good, solid validation data there. Let's now look at some practical application of all that. So here what I have in these particular rectangular plots here is the asphalt layer. And these are contours of damage. And on the top, you've got mechanical loading only after 20,000 cycles. So the asphalt's been subjected to 20,000 cycles. Notice where the localization of damage is. Damage localizes down here in the red, which is at the bottom of the asphalt layer, near the edge of the tire load. That's not a big surprise. Intuitively, we kind of figure that that's what's going to happen from layered elastic analysis. But now let's couple in the effect of moisture softening because of diffusion of moisture. Now we have two localizations of damage, one near the bottom, one near the top. So this might be a bottom-up crack, this could be a bottom-up crack, that could be a bottom-down crack. So this coupling of the environmental effects of moisture damage with the mechanical effects can be very valid. It's something that we really need to begin to focus on. And I'll interject at this point one question that somebody will always have in a presentation like this is, so what? That stuff is so computationally intensive, I would never be able to do it. But that doesn't mean that we as researchers don't need to strive to go the extra mile to see what's in the future and to keep moving towards a better system. Computational techniques are, of course, moving at a very rapid rate, and soon we will have the computational power to do this, even in a 3D mode, I'm confident. Now this is another localization model. In this particular case, what we've got is 4 asphalt segments. We've got a load under the arrows. We've got an unaged on the left upper, a 6 months on the right upper, and then a 60-month lower left, 120-month lower right. And we look at the evolution of damage. This is 8,000 load cycles, and you can see another change in the localization of damage. If it's undamaged, not as much damage, but it's still localizing near the bottom, and with the effect of the aging, as you would expect, it becomes more brittle, but where the critical area is near the surface, and it expands as the aging process occurs. I'd love to talk to you about the evolution function of the aging variable, state variable, but time does not permit that. As a matter of fact, I'm probably already getting close, and I'm not close to finish, so I need to hurry up. In the last year, we have been very fortunate to work with Dr. Navneet Garg at the FAA in their test facility there in New Jersey in Atlantic City, looking at the damage that's done by next generation of aircraft. And these next generation of aircraft that we're looking at have high tire pressures, heavy wheel loads, and of course they're tracking through that magnificent facility, doing accelerated testing there, and we're using Panda to evaluate the damage that goes on under those particular pavements. And I just wanted to talk to you about one point there. You know, we're looking at multiple wheel loads, so most of it has to be 3D simulation that we're dealing with high tire pressures. One thing that struck out to me when I looked at some of the initial data, these are vertical stress contours under the load of like a 777. And of course you can see that the asphalt layer is fairly thin in these sections, I think something like 5 inches. And then you've got the base and the subbase. But you can see, of course, that the vertical stress contours are high in the asphalt layer and very, very low in that subgrade, which is like a CBR subgrade, CBR3. But yet, if you look at, according to Panda, if you look at the viscoplastic strain that occurs in the pavement layers, even though those vertical stresses are high, the viscoplastic strain in the asphalt layer is negligible because it resists it, according to that plastic deformation model. But down here in the subgrade is where you really have the high viscoplastic strain. So that's where the rutting is occurring. Prior to looking at the FA sections, we were concentrating only on the asphalt layer. Certainly, with this kind of data, we have to turn our focus to the strain that's occurring, the plastic strain that's occurring in the sublayers. Marshall Thompson, Harold Tutumler would tell you that right off the bat without looking at this, with all the work that they've done on that at the University of Illinois and others. Bob Litton, but you know, this is something that we had to come up with as a good model for plastic deformation of these sublayers. So this is what we used. We tried many different models to try to mimic what occurred at the FAA test facility. And what we came up with was a modified Drucker-Prager with a cap. And that's nothing new. As a matter of fact, Drucker introduced that back in 1957. So we're not claiming that we came up with this model. We're just applying this model, probably a little bit of a modified version, to see if we can actually understand the data that we're getting from the FAA facility. And of course, if you look through this, you're going to find what happens if you have pure shear, what happens if you have pure densification, and where you have combination of shear and densification. But the key point here, the key point is simply that using only a Drucker-Prager type model without the cap, you'll never know if you're getting plastic deformation unless you're above the yield surface. And you'll never know if you're above that densification surface unless you apply the cap model to it. And that tells us that even if we're below the shear surface, if we're outside of that red curve, densification can occur. And looking at the data at the test site there in New Jersey, we found that much of the time it wasn't the shear stresses that caused that densification, but it was indeed the consolidation, the confinement that occurred in the subgrade that caused that densification. So here's a model of one of the aircraft that we evaluated, and our finite element matrix there. As you look here and look at the sigma 1,1, which is the confining stresses, you can see that they are very much lower when you get down here to the subgrade, only something like 14, 15 psi, much lower than they are, of course, in the asphalt and the near surface layers, but that's sufficient in a CBR subgrade according to our model to cause consolidation, which causes densification-induced plastic strain. So this model evaluates plastic strain in the sublayers, the unbound layers, due to both densification as well as shear stresses. And it takes both to mimic what's going on out there in the field. We tried to use this approach to actually calculate the rut depths that were occurring in 3 sections, LFC 1, LFC 2, and LFC 3. The only difference among the 3 sections is in all 3 sections the asphalt layer and the base layer are the same thickness and the same material. So there's no difference there. The only difference is the thickness of the subbase, and all the subbase is the same material. So just the thickness of the subbase. And as you would expect, you're going to get more rutting in LFC 1 than you will in 2 or 3 because of the higher stresses there. And that's exactly what we saw. But the kicker is not just that, but how much are they different and how well can you predict it. Got a little too much animation here. Could do without all of it. It shows pretty much the same thing. But what we see here is that we were actually able to predict the amount of rutting under a certain level of traffic, which was quite significant due to the subgrade deformation using the Drucker-Prager cap model. Quite different. This is about 2.3 something inches at the top and 1.5, 1.25. So a good bit of difference as the thickness of the subbase increases. And this is the way we were able to predict. We did a really good job in LCF1. As you can see, the line mimics the data pretty closely. LFC2, the data are the open circles. The blue line actually is the measured or the model response. And in LFC3, we weren't quite as good, but we can improve that by 3-dimensional modeling. This was just a 2-dimensional axisymmetric model. And I guess the key here is that we've got a fairly good model to evaluate plastic strain in the subgrade, and we certainly have to pay attention to that. We just can't focus on what's going on in the asphalt. One other test section that we looked at was with John Rushing. Dr. Rushing is a research engineer at ERDIC, the Engineering Development Research Center, and a former student of mine at Texas A&M under the Army Corps of Engineers PhD program. They ran some experiments under F-15 high-pressure tires and C-17 high-weight tires, lower pressure. And what was interesting to me there was we were able to predict rutting. The asphalt layer was designed to rut. The sublayers, in that case, were considered to be elastic in our analysis. They were very stiff and were not designed to rut. If you look at the cross-section, that's pretty much exactly what happened. And Panda was able to predict the level of rutting within very reasonable levels, 5 millimeters where actual was 7 for the 17, and 25 millimeters versus 29 for the for the F-15, the high tire pressure aircraft. But what was also impressive was if you look at the shape of the deflection basin, you can see the consolidation in the middle. You can also see the shearing and the pooching out here on the side due to that lateral shear stress movement. Pretty much mimics what you saw in the cross sections in the field. So that was rather pleasing. I want to give tribute here to Professor Kim, Young Rock Kim, at full Professor Young Rock Kim, by the way, at the University of Nebraska. He's taken this type of work, and I'm just going to spend a minute on it. This is his work, but he did a lot of it through the Asphalt Research Consortium, and he's very kind to share that work with us and allow us to take some credit for at least helping him get it done. He's taking he's coupling, if you will, or communicating between the micro-mechanical scale, the mixture scale, and what happens in the field. He calls the mixture scale the local scale, and he calls the pavement scale the global scale. So what he does is he has an idea of what the representative volume element, if you want to call it that, of the mixture looks like, the aggregate distribution, the aggregate shape, and so forth, the properties of the aggregate, the properties of the mastic, and the properties of the interface. So he's able to look at that, and what he does is he reads the input between the global and the local. He calculates a homogenized global tensor from the local scale. So he sort of takes the local scale and homogenizes it by taking an average of the data. And then he solves the global scale at some time interval we'll call T1. He applies the global solution back to the boundary volume problem at the local scale, and he iterates. He goes through various steps, various time functions, communicating back and forth, global to local, local to global. And that allows him to be able to work at the mixture scale, virtually work at the mixture scale by changing properties of the mastic, by changing properties of maybe the aggregate distribution, changing certain details of the mixture, and not being limited by laboratory tests, but to actually see how that will affect the pavement because we're communicating back and forth. The main point of communication there is going to be when the mixture becomes damaged because of some weakness in the composition of the mix, how does that play at the global scale? Because you're going to transmit that information, that stiffness information, for example, to the global scale. At the global scale, you're going to have different stress states that are going to be communicated back to the mixture scale. Here's an example of a paper that he wrote, and he was allowed to put my name on it because he felt sorry for me as an old professor. And at any rate, he did an analysis of I-80 there in Nebraska, and won't go through too much detail, but he identified 3 or 4 representative volume elements that are in different locations under the wheel load. And being under different locations under the wheel load, they're subjected to different stress states. So we're going to communicate that back to the mixture scale, and the mixture scale is going to consider how much damage is done and homogenize that and communicate that back to the global scale. So here's a little bit of an example, a little movie. I hope you can see it. We've got those elements that are located in different positions. One's right under the wheel, one's at the edge of the wheel, one's at the bottom of the AC layer, and one's way out here. And you can see the development of these damage areas that are developing into cracks, larger cracks. So what happens is that he uses a cohesive zone element the traction at the tip of the cohesive zone element identifies when a cohesive element is actually initiated, which can track the progression of cracks. Pretty ingenious method, and if you have any specific questions, I would encourage that you talk to him. So at this point in time, if I have time, if you have permission to have a little bit longer, I'm going to talk a little bit about some geochemistry for about 15 minutes. If that's allowable, then I'll let Errol to tell me. But at this point in time, I want to quickly review that what we've talked about so far is a template called Panda that characterizes the asphalt as viscoelastic, viscoplastic, nonlinear. Those are very important parameters. Panda is set in a template that is based on continuum damage mechanics. Continuum damage mechanics has some limitations, but its true value is that it allows us to couple other mechanisms with it. For example, moisture diffusion, weakening of the mastic, weakening of the asphalt aggregate interface because of moisture. It allows us to couple in the effects of aging, which harden the asphalt, making it more susceptible to damage. So when you couple in those effects with mechanical damage, you see shifts in the localization of damage. So we don't see exactly the same thing that we would see in, say, a layered elastic analysis. So that, I think, is the future. Is it computationally ready to go? It would be pretty difficult. It takes a lot of computer time. However, we're getting a standalone version and we're making it more efficient. But in the future, it's going to be there. And I truly believe that there's a great future in the multi-scaling, where we can link together the global or pavement scale with the mixture to see how fine-tuning the mixture can, virtually fine-tuning the mixture can make some big differences in what we see in the field. So that's where I'll stop on that, and with your permission, Errol, I'm going to go a little bit ahead. Well, I had one other component there. In this paper that Professor Kim prepared, he used this approach, the coupling between the micromechanical mixture scale and the global scale, and he did a simple parametric study. He said, okay, let's say that the mastic, we're going to use case 1, which is the standard reference mastic. Case 3 is going to be the standard reference mastic. Case 2, I'm going to reduce the mastic properties by 20%, lower them by 20%. Down here under tire loading, I'm going to have a standard tire load for cases 1 and 2. In case 3, I'm going to up it 30%. And then he evaluated, using this approach, relative rutting and relative cohesive element damage. And you can see that by increasing the, and looking at relative rutting, that case 2 is about equal with case 3, and about 40% more rutting in those two cases than the standard. Over here under damage, which is due to crack development in the cohesive zones, or the cohesive elements, you can see that cases 1 and 2 are about the same, but when you get to case 3, it's 5 times the amount of damage. What strikes me with this, if you compare that with equivalent axle load factors in ASCE 1993 design guide, this is a lot different. Because there you're looking at general serviceability change. Right? You're looking at serviceability change, because that's what the 93 design guide is based on, is delta PSI, change in serviceability, which is dominated by what? Subgrade rutting and roughness. Roughness first, subgrade rutting second. What is dominant, and cracking has very little to do with it in that 1.4 million load applications. Cracking was not a dominant factor. But where we're really interested in cracking, something like this can really help us understand it better. So it's a real advantage. Okay, so let's shift gears now and talk a little bit about something that I've always found very interesting, I love stabilization, chemical stabilization of soils. Done a lot of work with lime and cement over the years. And I know you've had a lecture in a previous section. I wish I was able to hear it. I was not, but back in the mid-80s, after Jim Mitchell gave the Terzaghi lecture on interesting effects, interesting phenomena in soils, one of the things he talked about was the heaving soils at Stewart Avenue in Las Vegas. And that had to do with lime and sulfate-rich soils. A year or so later, I was involved in Joe Pool Lake up in Arlington, Texas. So we can do all the great design and analysis of pavements we want to, but if we go in and stabilize a sulfate-bearing soil with a calcium-based stabilizer, we're willing to get something like this. Damage that you'd never get from heavy loads or environmental effects due to moisture or aging. That's terrible. So we got to do something about it. We have to address it. Here is a cross-section. And in this cross-section, you can see that what has happened is it probably more than just vertical movement, you have the accumulation of a lot of lateral strain. And that lateral strain has caused more of a thrust fault, where the sort of a passive earth pressure failure because of the movement over that pavement, the length of the lime stabilized layer. So what is causing this problem? Well, I'm sure by now most of you know as geotechnical engineers, you know that there's a material called ettringite, which is a calcium aluminate sulfate hydrate. And here are the components. Here are the reagents that go into ettringite on the left-hand side. And if you look at the molar volumes of those components, it takes 1 mole of tricalcium aluminate, or if you look at the moles that it takes to form 1 mole of ettringite, it takes 3 of C3A. C is a shorthand for calcium oxide. A is a shorthand for aluminate. So C3A, 1 mole, it takes 3 moles of gypsum. C, once again, for lime, S bar for sulfate, and H for water. And it takes 26 moles of water, a whole lot of water. And if you look at a picture of ettringite, it looks something like this, kind of a tubular structure with all of those compounds in there. And if you look at it under a scanning electron microscope, it looks like this, sort of a stalky material that's very anisotropic. Errol and I worked for years to get people to say anisotropic, but now they're saying it. Okay, so it works and it kind of expands dimensionally differently. So the first step that we did was to sort of, we went back to the Gibbs free energy principle, and we looked to our geochemist. And our geochemist said, well, you know, you can do something called a phase diagram, which allows you to evaluate for a particular mineral. If you can really identify what's in that particular mineral, it allows you to determine if ettringite is thermodynamically stable in that environment. And that's exactly what you see in these 2 diagrams. Probably hard to see at the back of the room, but this polygon right out here is ettringite. This polygon over here to the right is ettringite. So, a pH, when you add lime or cement to a soil, you're going to add it to get the pH up to above 12 so it will solubilize the minerals and react with them, the silica and the alumina. So the pH 12 is what I'm identifying here by that star. The locus of that star is a pH of a little above 12 and also a sulfate content of 3,000 parts per million, which we've sort of identified as an upper threshold. So at 3,000 parts per million, if I'm in this soil mineral, I am outside of the ettringite polygon, which means that some other mineral has a lower free energy than ettringite, and that other mineral will form ultimately. If my star is within the ettringite polygon, then it tells me that ettringite has the lowest free energy. So that's one way to evaluate whether or not you're going to have the potential for ettringite formation, and I don't have time to go into that in any more detail, but is a stability diagram, or to evaluate Gibbs free energy. Now, the other thing you can do is you can you can add things to your mineral. One thing that we found would be successful is you add soluble silica. Soluble silica means that you have the free energy to form something other than ettringite many times. And we found that adding some Class F fly ash or maybe some granulated ground blast furnace slag can often provide the silica to prevent the thermodynamic, to prevent the reaction causing ettringite to form. Here's something that we did in the lab that's quite interesting. Here we were just trying to test this ability, the power of the thermodynamic stability diagram. And in this particular case, we said, okay, monosulfide aluminate is a calcium sulfate aluminate compound that's low in alumina. And I'm sorry, it's high in alumina. And the ettringite is the tricalcium, it's the trisulfate form, that the sulfate ratio is high compared to the alumina ratio. So we said, well, what if you were to start with monosulfide aluminate and you took out, using some type of a process, and I can't go into that right now, you took out the alumina, would it show up in the stability diagram? And of course it does. And we also saw it in the experiment. We started out with the monosulfide aluminate, which is up here in the upper right, left. Wish this thing worked. And then down here in the ettringite is this. So once we were to capture the alumina, we actually saw the transition in terms of the micrograph. From there we said, well, that's really good, really fundamentally important, and we're going to get there. We're going to figure out how to use stability diagrams to help us prevent this, but right now we probably ought to focus on volumetrics. And it's not a really hard thing to do. We know the chemical formula for ettringite. We know how many moles of each component are in there. We can look in the literature and find the volume of a mole of that component, so we can calculate the volume change. And it's simply the molar volume of the products minus the molar volume of the reactants divided by the molar volume of the products. And when you go through that calculation, you find that if ettringite is fully activated by water coming in from the outside, you get a volume change of 135%. Okay? So that's where you come in with the stoichiometrics, and using that, you can easily come up with a percent change. If you have 3,000 parts per million, then the volume change is going to be a little bit less than 2%. If you have up to 5,000 parts per million, then the volume change is going to be a little bit around 3%. And based upon many other aspects of our study, we found that this 3%, 0.3%, 3,000 parts per million, if you develop that and don't allow any more sulfate to come in from the outside, then you're pretty safe, because those sulfates tend to fill the voids, but really don't give you too much trouble if you keep mobile sulfates from coming in from the outside. So that's pretty safe. If you go up to between 3,000 and 5,000 parts per million, you become a little bit more risky, but generally your system can accommodate that level of ettringite. You go above that, and you really have to do some special things to guard against it. So we use basic material science, geochemistry, for the phase diagram, coupled with stoichiometrics to figure out those initial values. And so back when we were dealing with the Denver airport in the mid to late 80s is when we were trying to come up with this stuff. And it's still pretty valid. Some of the things that we assumed in those days are not exactly right, but we fine-tune those. But our guidelines, which are in the report shown down here that I wrote with Sam Nair, NCHRP 144 and 145, less than 3,000 parts per million, your chances of having problems are low. Between 3 and 5, at least moderate. If you go up above that, you need to be very careful. So what we want to do, basically, if you have sulfate-bearing soils in this range, you want to add as much water as possible to activate the solution process of sulfate. You'll never add enough water to solubilize it because the solubility coefficient is too low. But you want to add enough to begin the process. So you start to nucleate crystals of ettringite, which form very rapidly if all constituents are available. You start to nucleate these points. And with any type of crystal, you have to nucleate before you can grow. So you nucleate the crystals and then the crystal growth occurs. So how do you maximize the rate of the crystal growth? Well, one way is to make sure that you continue to keep it wet, to keep it mobile, to keep it fluid. You mix it as much as you can to get a good intimate mixing, and you extend the mellowing period. Why do you want to extend the mellowing period? To give it time for as much of these crystal growth to occur before you compact it as possible, and also to make sure that you have used up as many of the constituents as possible. One final point there that is quite interesting. This is water-soluble sulfate. This is hours. So if I start out with a control and it's dry, you know, the soluble sulfates don't change. But if I get it a little above the plastic limit, I can find that I'm adding lime to it, by the way, didn't say that, but the water-soluble sulfates is going to drop from about a little over 1% down here to about a little over 0.5%. That's pretty good. But I can activate that process even more by adding an alumina source. See, ettringite is calcium aluminate sulfate hydrate. The alumina comes from the soil, and it's not going to be released until we solubilize alumina at that high pH, and that's a slow process. So how do you get this? How do you trick it? The way you trick it is you add a source of soluble alumina. And you can get some sources of soluble alumina that are readily available and that are quite reactive. And so what you see here is by adding about 12 grams of that alumina, and I can't remember what the size of the sample was offhand, but it really did activate the process. Now what's going on here to cause the water-soluble sulfate to drop? And if I get down to 3,000 parts per million, I'm pretty safe. If I compact it at this point, I'm pretty safe volumetrically. So what causes it to drop to that level? Well, it's the fact that the water-soluble sulfates are reacting to form ettringite. They're locked into the ettringite molecule, and they're no longer soluble to form more ettringite. So that's just kind of an example of how we look at this. These new materials very quickly, very, very quickly, I promise. One of the other compounds that we've been looking at is a terpolymer to stabilize soils. Now, terpolymer is a polyacrylamide base with an additive that has a cationic, an anionic, and a non-ionic component to it, thinking that those components will be able to interface with some part of the clay molecule, and hopefully the molecule is small enough to meander through into this interface between the clays. You can see the smectite type layer here, to meander in there and interconnect at those activation sites and stabilize the clay. And we did some fairly fancy techniques to evaluate that was the process. These particular pictures here are from Dr. Ding over in our soil science area, who's done some work on this in the past. And we were able to see, using the UV vis and X-ray diffraction, that the polymer was able to mobilize into those interstitial layers. And what's really neat about the polymer is that it can give you the same compressive strength as like Portland cement, shockingly. But it gives you a much less brittle material. If you do a fracture energy calculation, the fracture energy is about 3 times that of the cement stabilized material, meaning that its fatigue life is greatly enhanced. So we're still working to make sure that it's not susceptible to the effects of moisture, but this terpolymer and these types of polymers tend to have a lot of potential. And also the percentage of additive is shockingly small, about 2.5% versus maybe 4 and 5% for some of the other stabilizers. So something on the horizon that's pretty interesting. Okay, for the sake of time, I'm going to really quick kick to the summary. We have talked about a continuum damage model that has weaknesses, but it has the great strength of being able to couple different processes, like mechanical damage with moisture intrusion, moisture weakening because of moisture, the effects of aging, and so forth. It is a nonlinear viscoelastic, viscoplastic model, capable of coupling, as I said, capable of evaluating fatigue and healing, and capable of predicting plastic deformation, both in the asphalt layer and now in the granular layers. Multi-scaling, I gave you an example of multi-scaling. Using a model like Panda, for example, can accommodate both the local scale and the global scale. Refer you to the work of Professor Kim at University of Nebraska for more on that approach. We got off of that topic and talked a little bit about chemical soil stabilization. And one of the issues there that we talked about as an example was the fact that you're going to have certain problems that you run into, certain deleterious reactions. In these reactions, what we need to do is to be able to cross-cut, to apply the principles, fundamental principles of geochemistry and material science so that we can understand what's going on and make amends for it or make reparation for it. And then we talked a very little bit, about the idea that we're not stuck with what we have today. We need to use material science and these analytical techniques that our friends in soil science and geochemistry and basic chemistry use to come up with ways to understand the mechanisms. In this polymer study, we're working very closely with the molecular dynamics chemist, the geochemist, and the soil scientist in helping us understand these mechanisms. And that's the way we were able to understand how the terpolymer works its way into the matrix, the fact that it actually does, and why we're getting a material that has a substantially higher fatigue life and competes at the same compressive strength. We've got to work on making sure that moisture sensitivity is not a lingering problem out there, but we're getting there. So hopefully I've at least left you with the idea that fundamentals are important, theory is important, and as my good friend Bob Litton said, when questioned whether or not fundamental chemistry and physics were in the real world, he said they are the real world. So thank you for your attention.